Everyone got quiet right on time. Maybe you guys came early. Andy, shut up. Andy, some things to go straight. Just kidding. I love them. Guys. I put some things on the board from last class. So through it a little bit. Kind of not really sure. Kind of like I had like 1 or 2 lectures of my usual schedule, which is good. Give me a little flexibility to how I would teach angular minimum to you. And so I think the important thing is that since we have it fresh on the mind, we're going to just take a very, very, very small step away from our goal of determining the wave functions of hydrogen and the energy of hydrogen, and try to appreciate angular minimum just a bit more. And I don't want to embed a bunch of equations. You know, we're talking about these wave functions, these spherical harmonics, you know, the orbitals, S's and the P's and the D's, and we're eventually going to think about the map of those. But I'm a spectroscopist. I don't really think about orbitals all that often. I think about energy levels. I think about quantum numbers. I like simple things. And the nice thing about angular minimum is the quantum number math is really, really simple. The energy math is super simple. So I want to, in a sense, it's just 2 numbers, L and M. It's run, the equations are pretty easy. Anyone can calculate L plus 1. I want to kind of extend that and think about that, right? And build a little intuitive sense of how angular minimum works in quantum mechanics. And then we can maybe more appreciate the geometric aspects, the orbitals. So the idea is the electron is orbiting our proton, right? We're looking for these stable orbits. And the idea is that we're going to look at stable orbits at a fixed radius right now. And what we saw was that even at a fixed radius, there are lots of different choices for the angular minimum that I can have, right? L squared is a operator, like the total angular momentum of the electron, applied to our spherical harmonics, which are angular momentum wave functions for our electron, gives us back a h bar squared LL plus 1, where L is basically any integer greater than or equal to 0. And so that means at a fixed radius, you have, in some sense, an infinity of stable orbits. Not only do you have an infinity of stable orbits at different angular minimum, you have 2L plus 1 substable orbits. There's multiple stable orbits at fixed angular minimum that are noted by the M, right, which is the quantum number associated with the z direction of this angular, how it's rotating around the z direction. Right, I want to talk a little bit about that geometry. We only get these 2, and I kind of talked a little bit about the end of the class that L is a vector. Angular minimum is a vector. It has 3 components, and what I claimed is that we can only know 1 component. And so we just choose one. And in chemistry, we always choose the z direction. That's just tradition. And this is all I can know about the angular minimum. I can know roughly its direction in one axis. And I can know its total length, total angular minimum, but I can't know anything else about it. And so it doesn't really matter if I choose x, y, or z. But if I have a vector L, right, that vector L can be pointed anywhere along this blue circle here. Okay? They're all vectors that are pointing and have the same projection along z and the same length of L. So the electron can be orbiting kind of in any of those orientations corresponding to the angular momentum. And I can also just replace z with x or y. It doesn't matter. I get the same results. Just rotated my axes, a different one. And the indeterminacy of the 3 axes, the fact that the 3 axes are independent and you only know 1 is one of the reasons why when you have some fixed angular momentum, say I set L equal to 1, which is p orbitals, there are 3 of them corresponding to m equals -1, 0, and +1. And those correspond to trajectories along the x, the y, and the z axis. So the axes are all the same. Really no preference. I just know information about one of them. And so there's some ambiguity. And that ambiguity arises in the fact that you get, for a given angular minimum, you get the angular minimum L, you have 2L plus 1 stable orbits, right, which are the different orbitals, like p orbitals or d orbitals. Right, so Bohr, remember Bohr, Niels Bohr said that hydrogen has these stable orbits and they're all at different radii. There's one that's really close, there's the next one, there's the next one, there's the next one, right? It's like a planetary system, the classic picture of an atom, right? Is in some sense totally wrong, because what this is saying is I can fix my distance from the electron to the proton any distance I want, and even at that distance, I have an infinity of stable orbits to choose from. They're different energies, but there's an infinity. He always assumed that there's one per orbit, one per radius. So that's his key problem. And the consequence of that, right, is that this says that there are stable orbits with no angular momentum, right? It looks like the electron is not spinning. Kind of interesting. So I want to look at that. I want to give you an idea of how we prove that a hydrogen atom has a stable orbit that has no angular momentum. Really clever experiment that was done in the 1920s. And it's an experiment that people have done to many different things over the years. Pull up my notes for it so I don't get it wrong. Yes. So what I want to look at today is a really interesting effect, and that you can see in any molecule or atom, called the Zeeman effect. Okay, let me explain the Zeeman effect. You're going to maybe see similarities in this experiment, Peter Zeeman's experiment, to our initial deflection experiment from the first day of class, first homework. So the idea is very simple. We're going to have a vacuum chamber. All right, so we got a vacuum chamber. All right. Inside of that vacuum chamber, we're going to place a sample of dilute gas. It can be hydrogen atoms if you want. H atom gas. Could be any atom you want, but we'll pick hydrogen atom gas. So, right. Right. And what I'm going to do is apply a magnetic field to my sample. Right. So I put some coils, I wrap some coils around this chamber. These are magnetic coils. Okay, and I apply a field in this direction, up and down, the z direction. All right, so there's a field, a magnetic field, BZ, that's being applied in this direction, right? Just like our deflection experiment, our z deflection experiment, apply a z direct field. Right, and then on one end, I have an excitation source, maybe a laser. Right, so I've got a laser here, maybe, that interacts with the atoms. It's tunable. It has frequency h bar omega. And on the other end, I have a detector. Which goes to my sweet gaming PC. Okay, this is my detector. Okay, so I'm going to, just a reminder, I'm going to apply magnetic field B, which has just a Z component, 0, 0, BZ. Okay. With strength absolute value of BZ, right? Strength of the magnetic field. I can tune the strength of the magnetic field. I can turn the magnet up, I can turn it down. Okay, what Zeeman shows is that when you apply magnetic field, it shifts the energy levels of the angular momentum. And what you see, what he shows is that the energy, which is a function of L and M, is equal to the energy without the field. Energy, right? I'll write that down in a second. And it gets modified by a term proportional to a constant called G times mu B. This is called the magnetic moment. It's like the dipole, but for the hydrogen atom. Right? It's the magnetic dipole times the strength of the field, right? Times the M number for the state. Okay? And E naught, which is the energy of the state without any magnetic field, is h bar squared over 2m hydrogen, or sorry, 2me, sorry, it's the electron, L plus 1. Okay, so without the field, the energy of the electron, the orbital angular minimum, is the thing that's the energy depends. The faster the electron spins, the higher its energy, right? That's what we derived earlier. And so the energy only depends on L, right? In some sense, if L is 1, it doesn't really matter if you're rotating around the px orbital, around the x-axis, or the y-axis, or the z-axis. They're all the same. But what happens is that when we apply a field along the z-axis, now what will happen is the electron will prefer to oscillate with its angular minimum pointing with the magnetic field. And it will not want to oscillate pointing away from the magnet. Okay? Just like our z deflection, right? Remember our z deflection in our atom, and our electron, when we did those Stern-Gerlach experiments the first. The electron either associates, or the silver atom, if you will, either goes with the field or against the field. And it's the same idea for the electron and the atom. There are certain deflections or certain trajectories that align with the field and ones that are against the field. So let's see what we see in the spectrum. All right, so we'll go do an experiment. I'm going to do it on the next page. Well, so what we should expect is that depending on which orbital we're in, we'll get a different energy. Let's draw a little energy diagram. All right. And on the x-axis is the strength of the field. Okay, so we'll look at the energies of the states, angular minimum states at 0, right, and then onwards. Okay, and we have, right, we'll look at the first states, the 2s and the 2p, right? So the energy of the 1s state is right there, right, at 0. And the energy of the 2p states in this perspective is h bar squared over 2me times, well, it's just h bar squared over me, because L plus 1 is 2. Okay, and there are 3 states up there, right? There's px, py, and pz. So there's the m equals 0, the m equals -1, and then m equals +1 states here. And of course, the state down here is m equals 0. Right, so as you turn the field on, the energy of these orbitals, right, base energy gets modified by how strong the field is. So the states are going to start splitting out based on their m values. Right, so in the 1s state, we would expect to see no change, right? Because there's only one state, right? M equals 0, right? So there's no change there. So the energy due to Zeeman for this state is equal to 0, the change in energy. But the p states split. And so what we would expect to see is one state decreasing in energy by some amount. That would be the m equals -1, right? Because that makes this term negative, so the energy decreases. You would see the m equals +1 state split equally in the opposite direction, +1. And then there's an additional state in the center that doesn't change at all at m equals 0. So if we think about what the spectra look like for the absorptions, when we turn the magnetic field on and off, if the magnetic field is 0, right, the only transition we see is from m equals 0 to one of those states at intensity 3, roughly. Right, we would see a single line, right, that associated with the 1s orbital being excited to any of those states. They're all at the same energy, so they're all on top of each other. So we get a singlet. Right? And then if you turn the field on, right, the lines split out, right? And now they'll be at intensity 1 instead, because now each state represents a different level. Right? Each state has a different energy. Right? And so this would be m equals +1. This would be m equals 0. And m equals -1, right? And you get a triplet. Right? This is exactly what you see. This is what Zeeman saw when he did the experiment on it. As he turned the field up, he saw that this triplet gets wider. These two states basically spread out, and then the 0 state gets removed. There's a state in the middle in the triplet that just stays constant because the m equals 0 state is unaffected by the field. The only way for that to happen is if the ground state and the excited state have no angular momentum. 0. Or rather, the ground state has 0 angular momentum, right? So this is only the case, only true if the ground state, the 1s state, has L equals 0. Okay? So this is the proof that Bohr was wrong. And that if you apply a magnetic field to your molecule, your atom, it shows that you must have an initial state that has no angular momentum. The ground state has to be angular free. It doesn't change. It doesn't get affected by the magnetic field at all. So that means it has no angular momentum. Interesting. Right? And this is a completely general effect. I mean, it's not just hydrogen. Any system that has angular momentum is affected by the Zeeman effect for this exact reason. Okay, so that's our proof. All right, so we have states that have 0 angular momentum. Now the second question I have that's a little confusing is, why is it that we can only know Z? Why can't we know X and Y? Why is it that there's this indeterminacy in our orbitals? And you can make this argument that, and I kind of made this before, that these are wave functions of constant energy. Solve them assuming they have constant momentum squared. Kinetic energy is proportional to momentum squared. And remember that position and momentum are not compatible measurements. If you know the momentum, you don't know the position, and vice versa. And so if you have states of constant momentum or constant energy, then your states in some sense have no information about the X. So they're going to be equal. right? But that doesn't explain why they're not delocalized, why we can't know how delocalized they are around all three axes. Why do we only know one of them? It's a really, really interesting result. And I'll try to have you guys explore a little bit on the next homework. But I could show you an interesting theory, a theorem from quantum mechanics that we won't prove. And then I'll show you with just a book, a little exercise to show that why exactly angular minimum, you can only know one. Right? It's very interesting. So the theorem is this. So why is there no wave function such that Lx psi gives you mx psi, Ly psi gives you my psi, and Lz psi gives you mz psi simultaneously. Right? Why is it that we can't define a state that is valid for all three directions? That's one. The theorem we're going to use is called the I don't know what you want to call it. The commuting variables. No, sorry. So it's let me restart that. It's called CSCO, the complete set of commuting observables theorem. So let me explain what this means. I have a system, right? I have a hydrogen atom, and I want to determine what things I can measure about it simultaneously. Okay. I just want to make a big list, right? Just like we have before, right? You can measure position, momentum, angular momentum, you name it, right? A bunch of different things that you can write down. And as we can see, some of them are compatible, and some are not compatible. And the question, of course, is how can we determine whether two observables are compatible or not? Whether we can use the wave function to measure both things simultaneously. And there is a very nice theorem for it. The theorem is this. Consider two observables are two operators, A and B, such that A on some wave function gives you A sub n, psi n, and B psi n gives you B sub n, psi n. All right. So imagine we can define a wave function that gives us that we can measure both simultaneously. Okay. So they're both simultaneously measurable. A plus B are simultaneously measurable. Okay. Then we say A and B commute. All right. Let me explain what I mean by commute. Commutativity property in algebra says if you have a product x times y, that's the same as y times x, right? I can commute them, commute my variables, right? Multiplication is commutative, right? 2 times 3 is the same as 3 times 2. Okay, so what that is saying is that A, then B measuring psi, then A measuring psi. Right, so I measure B first and then A. So I put psi through my B box and then I put it through my A box. Gives me the same result as putting psi through A first and then putting it through B. Right, same result. Right, so the variables commute. Okay. Another way we write this is that A B minus B A is equal to 0. And if we want to be even more pedantic, we call this the commutator, which is a bracket A comma B. Right, this is just some notation. Right. Say that the commutator of A and B are 0. Okay, and all this is saying is I'm comparing the result of my measurement between measuring B first then A and A first then B. Right? You kind of did some work with this idea on the first problem set where I had you feed one thing through one box and then feed it through another, and then you swap the boxes and you saw that the result was the same or different. You're just evaluating commutators. This is like switching your Z box and your X box back and forth, right? And if the result is different or not. The result is not different, then we can define a wave function that's valid for both observables. If they don't commute, then we can't do it. Right? It's a really, really, really simple formula. It's a little harder to calculate, maybe, but it's kind of a simple idea. Why commutation has anything to do with this is a different question, but let me show you an example of this that we can do here in the classroom. All right, so let me give you an example. Rotations in 3 dimensions are not commutative. I show this to you really easily. Here's a book. Draw a book. So here's my book. Here's the front of the book. All right, notice that I have the orientation right side up and I'm facing straight away from you. All right, and we're going to define an axis system for this book. This. And I'm going to rotate the book through a sequence of rotations along different axes. And then we're going to swap them and see what happens. They're different. All right. So the first one I'm going to do, I'm going to go up like this. I'm just going to make up some. I know eventually I'm going to get this right. But I did this experiment in spectroscopy class last class. We were talking about symmetry and in spectroscopy, and I made some rotations and they actually did commute. So let me make sure I don't get them at this time. And so the first one we're going to do is a 180 degree or a pi rotation clockwise around z-axis. Okay, so what I'm going to do is rotate this along this axis 180 degrees clockwise. So that is this way, right? So now I'm at the back of the book. All right, so the result of this is back up. All right, now I'm going to do a 90 degree rotation counterclockwise. Well, counterclockwise around x-axis. Okay, this is the x-axis. Right, the way I had it was that, well, let's see, x-axis increasing in this way. Right, and I'm going to rotate around the x-axis, so it's going to be a flip pi over 2 counterclockwise. So that is this way. Right, so now you have the bottom of the book upside down. Look how talented I am, my friends. Let's flip it around. Let's do the same thing. We'll start from the same position and flip our order. All right. So pi clockwise, z-axis. Oh, sorry. That's the second one. Sorry. Pi over 2, x counterclockwise. Okay. That's here. This x-axis counterclockwise is this way. So now you have the bottom of the book up. All right. And then we're going to do pi z clockwise. Right? So that is this axis. And I'm going to go clockwise. Right? Just that. Right? And now you have the top upside down. Right? As you can see, 1 times 2 rotations is not the same as 2 times 1. Okay. Rotations are not commutative. Very simple proof. Some of them are. I just told you last class I came up with one that worked perfectly and commute. So some of them commute, some of them don't. But you can see that there are a set of rotations, in fact, quite a bit of them, combination rotations that are commutative. In 2 dimensions, they are commutative, right? In 2 dimensions, the only thing you have is this, right? And if I go this way and then undo it, go this way and this way, it's the same as going this way and this way, right? So in 2 dimensions, they're commutative. Only in 3 dimensions do they not commute. So 3D rotations are not commutative. Let's think a little bit about what angular momentum really is. Angular momentum is a rotation of a molecule around an axis. Right? So if you think about angular momentum as this big motion, this big circular motion, right? Think about doing those small rotations from angular momentum in very tiny little steps, little infinitesimally small steps. Right? And let's say you rotate around, you apply a little angular momentum around X, and then you apply a little angular momentum around Y. Right? And then you do the same thing but backwards. You apply a little angular momentum around Y, then you apply it around X, and you end up in a different spot. Because all you're doing when you're doing angular momentum is applying rotations in 3 dimensions. So angular momentum, as we say, angular momentum is created or generated from rotations. They have the same physics. They have the same geometry, symmetries, whatever you want to call it. Same behavior. Angular momentum is the physics of rotation. So rotation operators are, in some sense, little minuscule, infinitesimally small angular momentum operators, rotating by a small amount. And so if rotations are not commutative, then angular momentum cannot be commutative either. Because that's all angular momentum is, just rotations. Okay? So what that means is that rotations along the 3 axes of rotation are not commutative, and therefore the commutator is non-zero for any combination of them. And therefore, you can't know them simultaneously. Quantum mechanics is weird, but it's not that weird. It's still founded in real life things. They're just real life things that you don't really appreciate in macroscopic world. They become much more important in the microscopic world. These little things. These are things that we don't really get an appreciation for in Newtonian physics. Because in Newtonian physics, it doesn't really matter so much. Everything is like at some temperature and it's randomized. It's all classical. Everything's random. You're just taking averages. But here we don't have those anymore. Right? Everything's like in one state. Or no, thermodynamics doesn't exist. Thermodynamics, this is something that's relevant for one atom. You can't have a temperature for one atom. And so we have to start thinking about these fundamental properties of geometry, because that's what these little particles exist in. That's the world they live in, is the world of the fundamental relationships. So if rotations are not commutative, then angular momentum can't be commutative. Right. I'll have you guys play around with that a little bit in homework. Right? Fun things. Yeah. Not too much math. But let's connect this idea now. I've given you some ideas that tie us back to the first problem set. Right? Tie us back to Stern-Gerlach interconnection experiment. So let's formalize that connection. In fact, we have all the math we need to understand the Stern-Gerlach experiment, except for one thing. Okay, remember something let's compare the two different experiments. Let's go back to the Zeeman experiment. Right. Where I said, depending on how much L you put into the electron, into the hydrogen atom, how much angular momentum has, you get some level, you get some splittings. Right? And in the hydrogen atom, when you turn a magnetic field on, the deflection states, if you will, right? This is one deflecting with the field, one against, and one that's just traveling through the field. You get a triplet. If I went to L equals 2, which would be the 3D orbitals, for instance, the d orbitals, there would be 5. Right? Now go back to our deflection experiments with silver atoms or electrons. It doesn't matter which one. No matter what we did, there were always only 2 deflection states. There was an up and there was a down. There was never a center one, right? They never formed triplets. Right? But you can kind of see that this experiment, by applying a magnetic field and deflecting things to different energies, is very, very similar to that Stern-Gerlach deflection experiment. The same principle. But the results are different here. What the same in the hydrogen atom, you get, depending on how much angular momentum you have, you get some number of deflected states, different deflections. But when you do it to a silver atom in that experiment, or with an electron, you only get 2 results. You get 2. You don't get 3, you don't get 5, you only get 2 for the electron. And so it doesn't matter how much energy you put in that electron, you kick it go faster and faster and faster and faster, and it still only has 2 deflected states. So there's some other angular momentum, something else that's interacting that looks a lot, but it doesn't have this state structure where there's 1 state and then there's 3 states and then there's 5 states. It's some angular momentum where there's only 2 states, an up and a down. Right? There is no up and down here. I mean, there are up and down. This would be down, this would be up, or vice versa. And then there's also one that's nothing. So it's a different system. So there's another angular momentum that only has 2 components that's on top of this that the electron has. Or the silver atom does in the deflection experiment. Something that doesn't increase the number of states, but the math seems to work exactly the same. So this was an interesting result, and it's hard to appreciate how people figured this out without looking at the experiments. When we understand hydrogen, we'll be able to understand how they figured this out, because hydrogen holds the key to understanding the presence of this extra angular momentum that's in everything. And there's another type of angular momentum that systems have called spin. Now, I want to emphasize, and it's not immediately obvious why, but what we're going to see is that in some sense for the hydrogen atom, there are at least 2 sources of angular momentum. There's the orbital angular momentum, which is what we've been talking about. But as we'll see when we get to later on, to start to understand hydrogen a bit more, we'll understand there's another angular momentum that the electron has. And if you look closely enough, you'll realize that the nucleus also has an angular momentum. There's an additional angular momentum. It's in some sense what we're looking at is, if you think about the electron orbiting the proton, it is spinning around the proton. It's an orbital angular momentum, but the electron itself is also spinning on its axis. So it's like the Earth, right? The Earth spins and rotates itself as it rotates the Earth, or it rotates the sun, right? It rotates the sun once a year and rotates on its axis every 24 hours. In some sense, it looks like the electron in hydrogen also has it. That it is a rotating object that is orbiting something else. We'll see the consequences of that when we talk about hydrogen. But this other orbiting, this other rotation that the electron itself has, is called spin. Okay, and this is a intrinsic angular momentum. to held by almost every fundamental or microscopic particle. What we find is that when we go look at particles by themselves, like a proton by itself, or an electron by itself, or a neutron by itself, or boson, or the photon, or any particle, they all, or most of them, have that intrinsic angular momentum. They're all spinning on their own axis, or at least they have some behavior that looks like it. Unfortunately, it isn't like it's spinning on top of its axis. I kind of say that, but the math for that doesn't work, it turns out. It's more complicated. But it kind of looks like the electron is orbiting, and it has this special angular momentum that is angular momentum, but it doesn't work like all the other angular. Well, and what I mean by that is that there is no analog in the macroscopic world. This is a property of things only quantum mechanical. I just used I just rotated a book around a couple times to show you, to illustrate a quantum mechanical principle. This is a quantum mechanical principle of things that I can't pull a book out and show you an example. There's just no equivalent. So you just kind of have to accept it as is. And the best thing we can do is understand how it works and understand the structure of it, because it is very well structured. And predict, and understand the consequences. How does it affect chemistry? How does it affect spectrum? And spin affects all of these things, as we'll see. Right, and the important thing is that the total spin angular momentum is fixed. Okay, so what that means is that this intrinsic angular momentum spin, it's the length of the vector associated with it is the same length always. There aren't different L states. There's only one. It's got one length, and that's it. And each particle has a special length associated to that vector. Thankfully, most of them are all about the same. So some examples. The electron has spin 1/2. It has half a unit of angular momentum. We'll have to understand why that is in a second, because we've seen things that are 0, 1, 2, 3, 4, 5, 6 units of angular momentum. Here's one that's in between, kind of a weird number. But we see it a lot. The proton is also spin 1/2. The neutron is also spin 1/2. Interestingly, the photon is spin 1. All right, let's talk about the consequences of that. And atoms themselves have a spin, because atoms are made up of protons, neutrons, and electrons. All the spins add up together to make some net spin system. Some of them will cancel each other out. Some of the spins will be this direction, some of them will be this direction, and they cancel out. So you can add all the spins together for atoms, and you'll see that, for instance, the hydrogen atom is spin 1/2. The helium-4 atom is spin 1, but the helium-3 atom is spin 1/2. Carbon-12 is spin 0. It has no spin, but carbon-13 is spin 1/2. Interesting. So there's some atoms that have fractional spin, some atoms that have whole integer spin. Now, I think for your class, I gave you that lecture on the subatomic particles. And we talked about bosons and fermions. Those are particles that have integer spin and half integer spin. You can see that we have half integer spins. These are called fermions. And some that are integer spins, these are called bosons. Okay, they have different statistics and different properties, but we don't really have to worry about that too much right now. let's talk about how the math works. Why is it that it's 1/2? Well, we don't need to write down anything about wave functions for this stuff because these are angular momenta. We already know how it works. There is, because it's an angular momentum, it's in 3 dimensions. There's a s squared, right? There's an L squared operator, and there's a z-axis operator. It's 2 operators, just like there is for angular momentum. So we can define our spin wave functions, right, such that they satisfy, they measure s squared, and they give you back, just like before, h bar squared times some number s plus 1 times the wave function. And there's an sz operator that applies to the spin wave function, which gives us what we call h bar m sub s. We call it s for spin times the wave function. Right? Exactly the same behavior, exactly the same formulas as our orbital angular minimum. We just have a new number, s and m sub s, for the spin. Right? And so the spin angular momentum is just a fixed number. Right. And those numbers are the ones that I just wrote down, right? So for electrons, or for the H atom, or sorry, for the electron, let me just write the electron, right? S is 1/2, right? It's only 1/2. The only value it has, always spinning with this angular momentum on its own axis of 1/2 angular units of angular momentum. Just is. Just always is. Never turn it off. You can never make it bigger and make it smaller. Can't you? But it just always is. And so if S is 1/2, what does that mean? Just kind of block this off. For M sub S. Well, remember our rules from before. M sub S can be anything between S and plus S, right? Different by 1. Okay, so if S is 1/2, then M sub S can either be minus 1/2 or minus 1/2 plus 1, which is 1/2. So there are 2 spin states for electron, right? 2 spin orbits. There's a plus, an up, and a down. There we go. There's our deflection experiment. This is what the deflection experiment is on. Run electrons through the system, or silver atoms, which are also spin 1/2. They have this intrinsic angular momentum to them. And that angular momentum has 2 components, 1/2 and minus 1/2. So let's go back to the Zeeman experiment. And think what happens when we apply a magnetic field to that system. There are 2 spin states and only 2 spin states, 1/2 and minus 1/2. The energy is going to get modified by the value of that M, plus or minus. And so you're going to get one state that goes down in energy and one state that goes up in energy. You have an up deflecting and a down deflecting electron. So spin is the source of our deflections, and spin is just a product of this angular momentum that things have. Everything ties back together. This allows us now to, in some sense, we now have a construction, an exact construction that allows us to predict the results of the Sternberg experiments or the Zeeman. And you can see the connections between these 2 experiments, that magnetic fields interact with spins. And spin is a magnetic property of the system. The reason why things are magnetic in the first place is because of spins. The spin is the source of the magnetic moment for a particle. So the presence of spin, I don't have any room to put that on this board, but the presence of spin implies magnetism. Don't have magnetism without spin. And the interesting tell for that, so in some sense, the proof of that is that you can put all of these things in our deflection experiment. The electron goes up and down. The proton goes up and down. By the way, that's an NMR experiment. You do your magnetic resonance. That's all you're doing is you're doing the Zeeman effect, or a deflection experiment to the proton and the hydrogen atom. That's NMR. The neutron also has spin 1/2. We don't often study neutrons by themselves because they're unstable. That photon. Photons, we'll have to talk about photon spin in a second. That's a really interesting property. But here, look at carbon 12. Carbon 12 has spin 0. Carbon 12 is not magnetic. You run it through the Zeeman splitting or deflecting, and they don't deflect at all. No deflection because it has no spin. There is no magnetism in carbon 12. It's completely amagnetic because it has no spin. But carbon 13, you can do NMR on carbon 13. Just go upstairs and go do it on the NMR. Or NMR has a carbon 13 probe because carbon 13 is magnetic. Spin determines magnetism. Now, let's talk about the photon, light. What does it mean for light to have a spin? In some sense, photons, they're not really magnetic, right? Photons are emitted from magnetic interactions. Right? You have two electrons that interact with a magnetic force, an electron and a proton. They exchange, the way they exchange energy is through the exchange of photons. Photon carries energy between electrostatic particles. But photons themselves are not magnetic. So what gives? Why is it that photons have a spin but are not magnetic? Well, the reason why they're not magnetic is because they move at the speed of light. You can't create a magnetic field around something moving at the speed of light fast. So that's why, in some sense, there's other reasons, but the photon has no mass. It doesn't have a mass and it's moving at the speed of light. It can't have a magnetic field that other particles that are at rest can feel. Okay? So we don't care about that. So, but of course, how does the photons, if the photon doesn't install a magnetic field that we can feel around it, how does it show its spin properties? Right? How do we know it has a spin? Other than that Nikodym Poplawski tells us it does. And the idea is actually really, really cool. You guys, anyone who owns a pair of sunglasses takes advantage of the spin properties of photons. So photon spin states are called, and these were observed before quantum mechanics or photons even existed. Everyone knew what these were. They existed. You didn't know what it was. Are called polarization states. Right. Let's talk about polarization. Remember, electric field is a wave. It's got a field that propagates through space. Electric field. Right, it has a spatial component minus a temporal component. Right, so we can draw on an axis, right, the spatial component of the wave. And remember, it has two components. Plus the I sine kr minus omega t. It has a sine component that's perpendicular. That's the magnetic field. Right, this is E and this is B. Right, so you got this field. It's moving through space at some frequency and some wavelength. Right? Moving through the speed of light. Okay. That's a generic light wave. Now let's apply polarization to it. There are three, remember spin one means that there are, so if S is one, then M sub S, just like the p orbital can be -1, 0, and +1. Remember, these are angular momenta. So that means that there are two states where the photon is like spinning on its axis. And there's one state where it's not. And the way to think about this is pretty simple. So I'm going to draw I'm going to kind of do this at an angle for each one. Right? So here's our axis. We've got for m equals 0, you have the wave propagating on the axis like this. Right? And it's just moving down the line, just straight down the line, not doing anything. Okay, so you've got the ridges are just moving kind of linearly along the line. They're not rotating or anything, they're not moving, they're just moving straight. Okay. So you're like you can kind of, like if you're standing on top of it, you're just feeling the tops of the waves hit the top of your boots at the time it passes by. Okay, so it's just moving on a straight line. It's not doing anything besides moving on a straight line. Right, so we call that linear polarization. This is m equals 0. Linearly polarized light. Okay. Now, what about the other two? Well, the other two have some rotation to them. It's very hard for me to draw. But the idea is that the wave, the fronts of the wave are rotating around the axis. Right, so this, see if I can draw it, right? This is coming down here. And this is, let me do it in different color so you can see it. This is coming up. And this is coming down. Right? And this wave is coming up. And this wave is coming down, coming up, and so on and so forth, right? So what's happening as the wave is moving across this line, it's twisting. It's curving around the line. And basically, you're interchanging the magnetic field and the electric field in which direction they're applying. So the electric field goes into the imaginary plane, and the magnetic field comes into the real plane, and they rotate. Right? So there's a helicity. Say that it's like a helix. It has a helicity. And the term we call this is m equals 1. Right? And we would call this right circularly polarized light. Okay, it's moving in a clockwise fashion as it like a drill as it moves down. Right, should be obvious what the m equals -1 is. It's just going in the opposite direction. Right, so this is now going right ways instead. Right, this is left circularly. Well, I kind of screwed it up. Sorry, it goes the other way. Left circularly polarized light. Okay, so it rotates in the opposite helicity. Now, this is why polarized sunglasses work. Quite a bit, not all of it, but the light that, sorry, let me just say this. The light that the sun generates is randomly polarized, has no correlations to polarity. So 66% of the photon, I don't know if it's actually true, but some fraction of the photons that come out of the sun are circularly polarized. Say like 60%. let's just say roughly it's a third each way, right? It seems to be a fair way to think about it. And so what do we do with circularly polarized, what we have with circularly polarized sunglasses is that you have what's called a polarizer. It's a membrane, it's just a film that they apply to the sunglasses that only accepts light of a certain polarization. It's like it has an entry for light that only goes a certain way. And so what you do is you put a bright polarizer on the front of your glasses. There's a membrane or a film that has one polarization. And that says, I prefer light that has this polarization over this. And then what you do behind it is put a polarizer, another film of the opposite polarization. So anytime the right circularly polarized light goes into the left polarizer, it gets left polarized and gets canceled out by the right one, and vice versa. Right? So when you add a right circularly polarized signal to a left one, they cancel each other out. So what you do is you create polarizers, give you a bias towards one polarization, and then you apply one to the opposite polarization. And no matter what, you're going to cancel out all the circularly polarized light. Right? The right gets canceled out by the left gets canceled out by the right, and all you're left with is linearly polarized light. Okay, so that's where you get that free. That's a really free way to work with sunglasses, is you can just basically filter out 66% of the photons by filtering out two of the three spin states of the photon. Okay, this was developed in the 1800s, right? This is Maxwell, and I don't know if Newton knew about it, but Maxwell certainly knew. Faraday and these guys, they knew about polarization. Certainly Maxwell did, but they didn't have an appreciation for the physics of it. They just the physical. Okay, so this is an interesting example of spin. Magnetism is another product of spin. So there are, in some sense, macroscopic consequences for spin. Magnetism, polarization, NMR, quantum computing, for instance, is also due to this. Right? Those are consequences that we can build classical instruments to measure spin and do calculations and computations and manipulations with spin. There's ways to build instruments, but there's no equivalent angular momentum in an object that we can touch and feel. It isn't microscopic. Kind of interesting. Okay. Do I have anything else I want to talk about today? No. I think I'm just going to stop here. Let's do it. Let's finish it. It's a good place to stop. We'll come back. Now we're going to start talking about wave functions and angular momentum and start building towards hydrogen. We'll be back to that now. Now that we know that spin exists.
You want to see my
Once we have that picture, we'll be able to